Before we talk about implicit differentiation, it's important to understand the difference between what it means for an equation to be explicit versus implicit. All the sort of functions and equations we've dealt with so far have been explicit. So we want to start looking at dealing with more generalized equations that are implicit. So in other words, a function that is already solved for one variable, like y equals or f of x equals, that's explicit because it has one variable solved and everything else on the other side of the equation is another variable. If it's not like that, it's implicit. This happens when you have equations that have a mixture of different letters, or as we'll see later, geometric applications, right? Where we have geometric formulas that have more than one variable in them. We still want to be able to calculate the rates of change. And so we want to learn this new style of finding derivatives to help us do that. Now, to give you a couple examples of the differences, okay, on the left side, we have an implicit equation, right? Where we have a mixture of x and y's and neither of them is solved. Now, with one like this, you could get y by itself, or even x by itself, and make it explicit. Now, in those situations, you absolutely can do that and do the derivatives as we've been doing before. Even ones that look like this, right? This is the equation of a circle. Well, yeah, we definitely have some squares on the x's and y's, but you could still, if you wanted to, solve it explicitly. It may require, as you can see here, two different equations, right, for each part of the graph, but it can still happen. And certainly if that works for you and that helps you find the derivative, you can do it. But there are equations, as you can see here, where we have a mixture of variables, but we don't have the ability to isolate one, to write y equals only in terms of x or just x equals in terms of y. So because there's not an explicit form to it, we want to be able to calculate the derivative and figure out what that technique is, which is what we're talking about today. So in order to do this, we have to use what's called Leibniz notation. Something we've used before. It's obviously just some notation we've seen before, but we want to talk about how it actually works when you have an equation. So first off, you technically find the derivative of everything as you normally would. So the power rule, whatever you need, differentiate it. But every time you differentiate a letter, you have to multiply it times d that variable over dx. And the denominator there, that dx, really just means that's kind of the variable we're working with, kind of like the independent variable. So we say that's with respect to x. Now it's important to understand that while a lot of our examples are going to be dx, it's really any variable you want. In the future, we'll discover that we do a lot of implicit differentiation with respect to time. So we'll do a lot of dt, right? How is something changing as time goes by? But right now, we just want to master how to do this when we have those mixture of variables, right? So we can figure out what their derivative is. So the way it's going to work essentially is like this. In the past, if we had something very simple, for instance, like y equals x squared, right? When we did the derivative, we would often write, dy dx, the derivative of y is equal to 2x. But there was actually a step in between those things that took place, right? This is kind of the nuts and bolts of how Leibniz notation actually works. So technically what happens is you take the derivative of every single letter, as I've written, and we'll go ahead and multiply each one by the d that variable over dx. So by power rule, the derivative of y is actually just 1, and since I'm differentiating a y, we'll multiply that times dy dx. On the other side, just as always with power rule, the derivative of x squared is 2x, and technically you multiply times dx over dx. But when we look at what I've written here in red, we can simplify it. We don't need to write 1 times dy dx, and certainly dx divided by dx is equivalent to 1. So in the past, just treating it like notation, we kind of skipped right over here to the bottom. But to understand how we can do this with an implicit equation, you want to see how these things work. So going through the equation, we'll use whatever derivative rules we need to and differentiate each piece. And as we do it, we'll multiply each variable by d that variable over dx. Now, the only thing I don't have here written that kind of falls into place, though, is my final result is dy dx equals blank, okay? So there'll be times when we do this that we have multiple dy dx's showing up, and so after we differentiate, we do want to kind of clean things up and solve our final result here to say dy dx equals something. Okay, so let's try an example. So our first one, real straightforward, sort of the same thing we did before. So in this case, when I want to find the derivative of y, you go ahead and do that. And by power rule, it's 1, and then you multiply times dy dx. Over here, we have 3x squared, so its derivative is 6x, and multiply times dx dx. But of course, we don't have to write that. So to be honest, moving forward, the way I like to look at it is every single time that we find the derivative of any non-x, we can go ahead and just write that dy over dx. And anytime we differentiate something with x in it, go ahead and just do the regular derivative. If you want to just leave out dx over dx, that's fine. It definitely simplifies away. So anytime we're just doing respect to x, just do regular derivatives with x. And really just if you do a derivative of y, write times dy dx. So we can definitely see that in action here in our second example. The derivative of 2x to the third is going to be 6x squared. And again, technically times dx over dx, but I'm not going to write it. When I find the derivative of 3y squared, by power rule, that's the same idea. We're going to get the 6y to the first, but I do need to multiply it times dy dx. Now be careful, because when you see a constant, remember that derivative is still going to be 0. Okay, so let's look at an example that has a little more advanced rules, okay? This one has a chain rule on one side and a product rule on the other. And the reason I wanted to show this is that we still have to do the chain rule and product rule as normal. And really the only thing that's going to come up is within those rules, when at that moment we find the derivative of a y, that's the only time we have to multiply times dy dx, okay? So on our first one over here, if you need to rewrite that as the quantity raised to the 1/2, that's fine. But the derivative on the left side is going to be 1/2 times that whole quantity raised to the negative 1/2. Now, right now, I'm going to copy that inside, that y squared plus 5. I don't need to do anything else. It's only here on the outside, right, when I multiply times the derivative of this inside portion, that's when I'm going to need to multiply times dy dx, because that's when I'm actually differentiating the y. So I've done the outside layer. The derivative of the inside is going to be 2y, and that needs to be multiplied dy dx. Now on the other side, we have a product, right? We have the x squared times y. So within this product rule, I'm going to do my normal steps, but at that moment when derivative of the y comes up, that's when I'm going to multiply times dy dx. So in this case, the derivative of the first one is going to be 2x times the second one, y, plus the derivative of y is 1 times x squared, and on this term, and only that term, we need to multiply the dy dx, because that's where the actual derivative of y happened. Over here in the first part, it was just copied, so you don't need it. And of course, remember that we have a plus 1. Now, with the other thing that makes this question a little bit extra compared to our last ones is that at the end, we definitely want to say dy dx equals. We want to get it by itself. So I need to solve for it, which means I'm going to take the term over here on the right that has a dy dx in it and subtract it over here so I can combine all the dy dx terms. At the same time, I'm also going to take this 1/2 and 2 and kind of simplify those to make it look a little nicer. So on the left side here, I'm going to have, when I put the 1/2 and the 2 together, just a y squared plus 5 raised to the 1/2, so that's still there. Okay, we multiply times a y, and then that still has a dy dx on it, and I'm going to subtract this term over. So we'll subtract from that x squared dy dx. And then what that does, of course, is it helps me make sure all my dy dx stuff is on the same side. Now remember, over here on the right, I still have this 2xy, so that's going to remain. And so in order to get dy dx by itself, what I need to do is look at these two kind of terms and factor it out. So you'll discover a lot of these are, collect all your terms with dy dx, factor and divide. So my last step here is I'm going to factor out the common dy dx that's in both those terms. And what that leaves me with is this y squared plus 5 raised to the negative 1/2 power. Got my negative there. Times y, and there is a minus x squared in the next term, and that equals my 2xy, which means at the end when I put all this together and solve just for dy dx, I'm going to divide all of this stuff over here. So that means at the end of the day, when I do all my work, the rate of change of y with respect to x is going to be that 2xy over there on the right divided by all this stuff, okay, which is my y squared plus 5 raised to the negative 1/2 power times y minus x squared. Now, if you want to do a little bit more simplifying to clean up, you can, but at the end of the day, at minimum, we want to make that dy dx by itself. So let's try one more example, this time involving a trigonometric derivative. It is still a chain rule because we have stuff inside of it, but again, what I want to emphasize here is that the only time you multiply times the dy dx is when you actually differentiate the y as you get to that inside layer. All right, so the outside is tangent, whose derivative is secant squared. So there's our outside derivative. We'll copy the x plus y, then multiply times its derivative. The derivative of x is 1. The derivative of y is also 1, but that's the one piece we have to multiply times dy dx. On the other side, the x has the same derivative, which is going to be 1. Now, what makes this one a little bit different is in order to get the dy dx by itself, I have to divide the secant over, then subtract the 1. So it's going to be a couple steps, but I'm going to do them all here in one. So at the end of the day, when I get the dy dx all by itself, okay, we're going to divide the secant squared over, and 1 divided by secant squared is the same thing as cosine squared, because they're reciprocals. So I can make it a little bit nicer if I do that, and then subtract 1 to get the dy dx by itself. Now, the last thing we want to talk about is something we're going to use kind of in the future. But just because we're learning this new kind of style of differentiation, we want to get a little practice with it. So the examples we've been doing so far have been just simply finding the derivative with respect to x, which is fine. And normally we do that a lot. But we also want to be able to do it with respect to any letter. Now, what's going to be different here is that I've chosen to find the derivative of these equations with respect to t, which oftentimes will be time in our context. So that means that every single time we differentiate any of these variables, we have to multiply it times d that variable over dt. So what's going to be different here is that it's not just the y's, but also the x's that are going to have that happen. So if we look at our first example, y equals 3x squared, again, we're going to differentiate everything, but each letter is going to have a d over dt multiplied by it as I differentiate. So the derivative of y is 1 times not dy dx, but dy dt. And that stands for the rate of change of y with respect to the change in time. On the other side, 3x squared becomes 6x, and this does need to be multiplied times dx dt, as that talks about the rate of change of x with respect to time. So as you can see, we actually have multiple derivatives showing up because neither of them simplify to 1 like it did earlier with dx over dx, and that's okay. You'll discover later that there are going to be equations where we need multiple derivatives to talk about how one variable is changing in relation to another. Now, if you're wondering what kind of context that looks like, look at the second example. This is the real basic equation for the area of a circle. So it's a equals pi r squared. So what I'm going to do is I'm actually going to find the derivative of the equation of the area of a circle, and what that does is it provides me a relationship between the rate of change of the circle's area compared to how fast its radius is changing. So if I go ahead and find the derivative of a, by power rule, that's just 1. But because I'm finding the derivative of a, it's 1 times dA dt, which stands for the rate of change of the area with respect to time. To find the derivative of pi r squared, that's just a number times r squared. So by power rule, that'll be 2 times pi, and r becomes the first power. And since I'm differentiating in r, we multiply times dr dt. So as you can see, we now have this equation here in green that tells me that the rate of change of the area of a circle as time goes by is equal to its 2 pi r times the rate of change of its radius.